Hello everyone. Today we're going to embark on a journey from surface phenomena to underlying truths, exploring how we can achieve business excellence through Six Sigma and statistical validation. Let's start by looking at the essence of work and the core equation Y equals F of X. Y represents effectiveness, which is the right goal and the right thing we need to accomplish. F of X stands for efficiency, the correct methods and processes to reach that goal. Now, let's break down the relationship between effectiveness and efficiency. If we're doing the wrong thing the right way, or the wrong thing the wrong way, we're not on the right track. What we truly aim for is doing the right thing the right way, though we might also face the situation of doing the right thing the wrong way, which we need to correct. Now, let's talk about redefining problems and the path to deriving them. The Chinese character when in problem means a question raised at the door, the start of exploration. The character Ti means a clear mark on the forehead, a core goal that everyone can recognize. To get to a solution, we follow this path, starting from a point of contention, narrowing it down to a contentious topic, then to a clear topic, framing it into a specific problem, and finally working towards an answer. Next, we'll explore the three dimensions of work objectives. Step 1 is standardization, similar to basic learning in school. It's about repeating tasks accurately without mistakes, just like following fixed arithmetic operations. Step 2 is for specific purposes, which is what most general enterprises focus on. It means breaking out of fixed frameworks to seek creative solutions. Step 3 is hypothesis validation, which is for expert groups. It involves setting multi-dimensional goals in uncharted areas, measuring and managing them on our own to uncover the truth. Now, let's cover the three fundamental thinking approaches for strategic thinking. First is tree thinking. It's a hierarchical way of thinking that breaks down complex problems systematically from top to bottom. Second is matrix thinking. This approach classifies objects in multiple dimensions and conducts cross-analysis to develop clear strategies. Third is process thinking, which is the core of Six Sigma and DFSS. It focuses on controlling results through the flow of input, process, and output. Let's put matrix thinking into practice by looking at awareness and ability. We'll analyze the relationship between having ability or lacking ability and having awareness or lacking awareness. First, there's the state where you have ability but lack awareness. Second, the ideal state where you have both ability and awareness. Third, the state where you have neither awareness nor ability. Fourth, the state where you have awareness but lack the necessary ability. Now, let's discuss the three perspectives for practical problem solving. First is cause-effect analysis. This involves tracing back from results to find the root cause or predicting the final impact from a given cause. Second is benchmarking. By observing mature experiences and leading exemplary cases, we can find the direction for breakthroughs. Third is future prediction. Based on current information and trends, we proactively envision upcoming changes and prepare for them. Let's start with the basics of phenomenon analysis, objects and defects. These are the two core axes of a difference description, which helps us grasp the essence of a phenomenon. First, the object. We need to clearly define what exactly we're talking about. Second, the defect. We need to specify exactly what problem has occurred. These two elements are interdependent, meaning they rely on each other to fully describe the phenomenon. Now, let's structure information using the FW1H framework. We'll compare facts that occurred with unoccurred facts, which act as a control group. For what, we'll identify the object or defect that did occur and the one that didn't. For where, we'll note the location or part where the event happened and where it didn't. For when, we'll record the time or situation of the occurrence and the non-occurrence. For status or how, we'll look at the quantity or trend of the occurrence and the non-occurrence. The key to precisely isolating a phenomenon is not only identifying what happened, but also clearly defining what did not happen. Now, let's move from qualitative to quantitative analysis, connecting abstract phenomena to quantitative metrics through QFD, or quality function deployment. Abstract phenomena can be prioritized into primary, secondary, and tertiary levels. Using QFD, we can translate these abstract concepts into measurable quantitative metrics, which we denote as y sub 1, y sub 2, up to y sub n. Only when we quantify phenomena can we establish the foundation to calculate metrics like mean, deviation, and DPMO, which stands for defects per million opportunities. The purpose of quantification is to understand populations and samples, which is the first step to accurately break down and verify our target y through the path f of x. A population represents the absolute truth, and we use metrics like population mean, population variance, and population standard deviation to describe it. A sample is an approximation of the population, and we use sample mean, sample variance, and sample standard deviation for it. We obtain samples through sampling. Statistical metrics are tools that help us get closer to the truth of the population. Now, let's dissect data into parametric and non-parametric types. First, parameters are data that represent the core characteristics of an entire population. There are two subtypes: continuous data, which are precise, numerical values obtained through professional measuring instruments, like length or weight, and discrete or categorical data, which are count-based values derived artificially, like the number of defective items. Then, non-parameter data refers to data that doesn't assume a specific distribution, such as rankings or signs. We use it for basic analysis when data is limited. Here's a matrix to help us choose the right analysis technique. If our dependent variable y is continuous and our independent variable x is continuous, we can use correlation analysis or regression analysis. If y is continuous and x is discrete, we can use t-test or ANOVA, which stands for analysis of variance. If y is discrete and x is continuous, logistic regression or discriminant analysis are suitable. If both y and x are discrete, we can use proportion analysis or chi-square test. Now, let's talk about hypothesis testing, a statistical method to find truth from unknown data. It allows us to infer the truth of an entire population using sample data and determine whether our prediction whether a change in x will alter y holds true. First, the null hypothesis, denoted as HO, is the conservative assumption that maintains the status quo. It claims there is no change or there is no difference, and it's the claim we aim to refute. Then, the alternative hypothesis, denoted as H1, is the new claim we want to prove. It states there is a change or there is a difference. Now, let's discuss risk management through significance level and p-value. The significance level, usually set at alpha equals 0.05, is the maximum risk boundary of error we are willing to accept. The p-value is the actual risk cost we bear when we reject the null hypothesis HO. The conclusion is, if the p-value is smaller than the set significance level alpha, we reject the existing state HO and adopt the new truth H1. This area where we reject HO is called the rejection region. This is a data collection plan template. It includes columns for metrics, which are the measures we track. Data type, which specifies whether the data is continuous or discrete. LSL, or lower specification limit. Target value. And USL, or upper specification limit. Below the table, we also need to record long-term and short-term Z values, equipment repeatability, and DPMO, which is defect per million opportunities. This plan helps us systematically organize and collect the data we need for analysis. Now, let's look at the complete loop of problem solving. It starts with capturing the voice of the customer, or VOC. Then we derive core topics, grasp the phenomenon at hand, uncover the root cause, quantify the problem with numerical data, and finally develop execution tasks. Only objective truths supported by data and statistics can prevent errors caused by reliance on experience alone. You might be asking, why focus on Six Sigma? Let's talk about the trap of averages. A common misconception is that the average from daily sampling tells the whole truth, but that's not the case. The truth isn't in the mean, it's hidden in the dispersion and variance of the data. Now, let's explore the truth behind normal distribution and sigma levels. At 1 sigma, we have about 700,000 defects per million opportunities, or DPMO. At 6 sigma, that number drops to just 3 points for DPMO. As the sigma value, or Z value, increases, the process becomes more robust and the probability of defects decreases exponentially. Let's look at a practical example, the variance in 500 milliliters bottled spring water. When we measure 500 milliliters bake sand spring water, a representative sample of data will inevitably have minor errors and follow a normal distribution. Our goal isn't to eliminate errors entirely, it's to drastically reduce the range of dispersion within a scope that satisfies customer demands. Our ultimate goal is to control dispersion. We have a target value, an LSL, which is the lower specification limit, and a USL, which is the upper specification limit. To achieve this goal, we need to follow 3 steps. First, center the data around the target value. Second, shrink the variance to narrow the dispersion. Third, implement controls to keep the process stable.